Welcome back to ChemExam Explained, where the aim is chemistry clarity, exam mastery. In this video, we will be looking at Cape Chemistry, Paper 2, Unit 1, Module 3, 2025. Let's go. 3, Part A. Table 3 shows the variation in some physical properties of group 4 elements. Now, all we are required to do is to look at the table and observe the trends and then describe what each of the following trend is saying. So part 1, describe the trend in each of the following. Electrical conductivity from silicon to lead. So in looking at silicon to lead in electrical conductivity, we're observing the trend here. And so you can see that from that trend, electrical conductivity increases from silicon to tin, then decreases from tin to lead. The melting point from silicon to lead. Again, you come here in the table and you look at the melting point from silicon to lead. And you can see that the melting point decreases from silicon to tin, then increases from tin to lead. That is all the question is asking you for, to describe what you're seeing with respect to the trend. 3A Part 2. Account for the variation in melting point from carbon to tin in terms of structure and bonding. Well, carbon has giant atomic structure where the carbon atoms are bonded covalently, giving the structure a high melting point. So this is strong atomic or strong giant atomic bonds. And these bonds are very strong, and therefore the melting point will be very high there. Going from silicon to germanium, these are metalloids, and these have larger atomic radii with weaker bonds. Now, if you have larger atomic radii, your bond length increases, which makes the bond weaker and thus lower melting point. Going from, or looking at now, tin and lead, they have metallic bonds with exceptionally low melting point due to only 2 of the 4 electrons being involved in bonding. So 2 of the electrons cannot move because they are held onto by the nucleus very strongly. And this is called the inert pair effect. And the other 2 will be lost to the sea of electrons and flow throughout the cations. And so that is why only 2 valence electrons are involved in bonding. And so the attraction now between those cations and those 2 electrons are weaker than the bonds in the giant structures, and therefore the lower melting point for tin and lead. B Part 1. Describe the reaction of lead 4 chloride with water. So this is our tetrachloride. So PbCl4 reacts with water through hydrolysis to form a white precipitate of lead 4 oxide or lead dioxide and an acidic fumes of HCl gas. B Part 2. Write the balance equation for the reaction described in B Part 1. So here we have PbCl4 reacting with water, and through hydrolysis you form our lead 4 oxide, aka lead dioxide, and our HCl gas, which is our acidic fume. And of course, the lead 4 oxide is our white precipitate. 3 Part C. Table 4 shows some physical properties of group 2 elements. And here we have the various properties: density, atomic radii, ionic radii. C Part 1. State the trend in each of the following from beryllium to barium. Density. Just checking out the density, you'll see that the density decreases from beryllium to calcium, then increase to barium. Atomic radii. The atomic radii increases down the group from beryllium to barium. C Part 2. Account for the trend in atomic radii in terms of the nuclear charge and the screening effect, which is same as the shielding effect. The number of filled shells increases down the group, which leads to more screening of outer electrons. The increase in nuclear charge has little effect on the outer electrons due to the screening effect, so the atomic radii increases. D Part 1. Complete the table below by recording the observations that would be made when a 1 molar solution of sodium sulfate is added to 0.1 mole per dm cube of each of the group 2 elements. So the group 2 cations would be magnesium ion, calcium ion, strontium ion, and barium ion. And these are all 2 plus because they belong to group 2. We should know that the solubility of the group 2 elements decreases down the group. And so when you react sodium sulfate, which is aqueous and soluble, with our barium ions, our magnesium ions, the strontium ions, Sr, and the calcium ion, you'll see that these ions are combining with the sulfate from the sodium sulfate. And so you should observe precipitate of various size or no precipitate. So we know that the solubility of sulfates decreases down the group. So the most soluble sulfate would be the ones at the top, and the least soluble ones would be the ones at the bottom. So magnesium sulfate would not produce any precipitate. But as we go down the group, due to the fact that solubility decreases, you'll now have a thin white precipitate. And then you'd have a medium white precipitate. We could put the term medium just to compare the sizes of the precipitate. And here you have a dense or large amount of precipitate as you produce barium sulfate. So going from magnesium sulfate, no precipitate, to small amount of calcium sulfate, to more than calcium sulfate for strontium sulfate. And of course, barium sulfate, being the least soluble, would produce the largest amount of precipitate. And that would answer our question for this table, knowing the fact that the solubility of sulfate decreases down the group. Part 2. Account for the observation in D Part 1. As the cations get larger, it has a lower charge density. Therefore, it becomes less attracted to the polar water molecule. The ionic lattice is harder to break. That is, lattice enthalpy is greater than hydration enthalpy. Therefore, the solution is more endothermic. That is, less soluble. Part 3. Write the ionic equation for the reaction between the barium ion Ba2+ and 1 more sodium sulfate solution. And as you saw the examples up here, you simply write barium 2+ plus SO4 2- to produce BaSO4 solid. And this is a perfect example of how you can test for the presence of barium ions using sulfate ions. Part E. Part E. Some compounds of aluminum, calcium, and magnesium have various uses. For any two of the metals, complete the following table by naming one compound of the metal and the use of the compound. So here we have a few of them. Even though they require one, here we have a few of them. So we have magnesium in the form of magnesium oxide can be used as the lining of furnaces because it is ionic and therefore would require a large amount of heat for it to be broken down. Calcium in the form of calcium oxide can be used to raise the acidity of soil because when the soil is acidic, the plants cannot grow in the low pH, so it can be used to increase the pH of the soil. Aluminum oxide can be used as an abrasive in the vehicle bodywork. And of course, it can be used in window frames. We have other examples. Magnesium hydroxide can be used in toothpaste or an antacid, specifically the milk of magnesia. Magnesium sulfate is a laxative and it can be used as Epsom salt. Calcium carbonate can be used in cement, and of course, calcium sulfate can be used in mortar or plaster of Paris. And the plaster of Paris is when you get your hand broken or your legs broken, the plaster they put on it is called plaster of Paris, and it is calcium sulfate. This ends Module 3, Question 3 of Unit 1, Paper 2, 2025.